get started. So welcome to this first technical session of the second day. I'm Patrick Studi. I'll be the chair for this session. We have 3 talks. As usual, there will be 3 to 4 minutes and some questions afterwards. So let me put the slides. This is the first talk. Yes, so the first speaker is Shou Chen. I hope this is the right pronouncement. So he's a fourth-year PhD student from UC Santa Cruz, and he's working on distributed systems, cloud computing, routing, quantum networks, sounds interesting, and network security. So I know it's 8 o'clock in Santa Cruz, so pretty early to give a talk. So looking forward to hear that talk. Let me get the slides up. So, and we are ready. Oh, okay, I need to share the screen as well. Sorry. Can you see the slides?
I can.
Okay, so yeah, go ahead and let me know when you want me to turn the page.
Great. Thank you for the introduction, and your pronunciation of my name is very good. It's the best. Thank you. So hi everyone, I'm Shou Chen from UC Santa Cruz. I will talk about Kinkery, fast and lightweight software cloud load balancer. It's a joint work with Ye, Minhao, Xin, Yin, Xiaozhou, and Prof. Chen Tian. Next slide, please. Next slide, please.
Yeah.
So the first question is, what is a load balancer? So this gateway in the middle works as a load balancer. It sits between the clients and the multiple backend servers, and it distributes each request to the right server and balances the load across the servers. The load balancer publishes a single external IP address as a web service, and the IP address is called virtual IP or VIP. And each of the backend server has an internal IP, or called direct IP or DIP. Next slide, please. So we list the 3 major performance challenges for cloud load balancers. First is the throughput of the load balancer should be very high to support a basic cloud. Second, there are a huge number of connections and connecting the cloud and the outside. And another challenge is that per connection consistency, also called PCC. That means all packets in the single transport layer connection should be directed to a single DIP, or the connection breaks if it doesn't follow that rule, like the second arrow in this figure. Next, please. The existing solutions involve software solutions such as hashing and hash table, and hardware approaches and stateless approaches. Next, please. We propose Kinkery, which is fast, compact, while preserves PCC. Besides, Kinkery supports weighted load balancing, where the DIPs are heterogeneous. Let's see some numerical results. Next, please. Sorry, can you go back? Thank you. The processing throughput of load balancing algorithm characterizes its capacity. This figure shows the throughput of the load balancing algorithm of Kinkery and other alternative algorithms in a large network. A Concurry maintains more than 2 times the advantage in throughput in all network sizes. Next, please. This figure shows the weighted load balancing for heterogeneous backend servers. Using Concurry, the measure is always close to 1, which is the best setting. When there are weighted changes, the measure increases temporarily and quickly returns back. Next, please. This figure shows the memory cost of the Concurry, Maglev, and Silk Road. Concurry is the most compact one and uses less than 50 megabytes for 16 million packets. Concurry is very efficient in memory footprint and thus can be ported to the hardware switches. Next, please. Yeah, Concurry is a portable solution and does not rely on any specific platform. It is deployed in a real network with DPDK. Also, a P4 version is available to run on compatible programmable switches. Next, please. As a conclusion, Concurry is a portable to many platforms, and Concurry is fast in lookup while keeping a compact memory footprint and per connection consistency. And the Concurry provides weighted load balancing for heterogeneous DIPs. Thank you for listening. Next, please. So that's all my talk.
Yeah, great. Thanks for this short talk. Let's see what questions we have. There is one question that has been submitted. That person asks, when a whip fails, it looks like Othello redirects all the connections to another whip, but aren't all the whips in front of the Concurry data plane? And so that means the client essentially would have to handle this?
So I understand the question is that what will happen if the load balancer itself breaks?
Right. Yes.
Right? Actually, the load balancer can be duplicated to many copies, so that one failure in the load balancer doesn't result in total failure of the whole system, and the load balancer itself doesn't contain some state like how the connections are mapped to the backend servers. So if the front end load balancer breaks, it doesn't hurt the robust of the system.
Okay, so a follow-up question from my end. So what about the consistency if a load balancer fails? Will the new connections be routed to the same dips?
So you the second question also focuses on what will happen if the load balancer fails.
Yeah.
So if the load balancer itself fails, the takeovers should be should be able to take the control. Like no, it's not a control. Like the traffic will go through the standby load balancer, and actually there's no problem in the data plane. Like the data plane itself doesn't contain the state. It's because of our unique design. We don't store the state in the data plane. So a single load balancer failure doesn't result in any system total failure or some traffic going through a different date. That won't happen.
Okay. And so did you evaluate this with a set of real applications in practice? You have some real applications that are good candidates for this?
Candidate?
Yeah.
we did research and we found that the maglev and the Silk Road are two very competitive alternatives, and but Silk Road itself is focuses on the hardware programmable switch. So that means the Silk Road is designed to run on a P4 compatible hardware switch. And so their algorithm may be not optimized on a software load balancer. But the maglev is designed for a software load balancer, and we compare our solution with these two solutions. So our solution is called Kinkery. So we compare Kinkery with maglev and Silk Road, all on a software server, because we currently don't have access to the programmable hardware switch, and so we saw some numerical results in the slides. They are all comparisons between Kinkery and Silk Road and maglev, or some compatible algorithms like the maglev is not open source, and the Silk Road is dedicated for the P4 switch. So we implemented these two algorithms on according to the paper description, and we did our best to reproduce the results or the algorithm, and we hope we are precise.
Yeah, thanks for the answer. So I actually also wanted to ask regarding, you mentioned the P4 and the DPTK implementation. Would it make sense to actually have an implementation based on Berkeley packet filters as well?
Berkeley packet filters?
BPF, the Linux support for sending small programs down to the kernel and intercept packets in the kernel. So you could do, I don't know, you could maybe do the hashing and so on directly in the kernel. That's just a question. If that would be another alternative implementation of this.
I see. That sounds like a very interesting application, and but we didn't get a chance to run our algorithm on that, and maybe we could try. But I have one comment before I try this. It's like a modification on the kernel. Maybe we can offload some functions to the kernel, like the network driver or network stack in the Linux kernel. But I think it may be not the optimal choice, because we use DPTK that is dedicatedly designed for kernel bypassing, because the kernel itself is slow in the forwarding. And if we have a chance, we can have a try, and we compare the solution between the DPTK and the Berkeley one.
Right. Yeah, with the Berkeley packet filters, you also would try to make it, I mean, you would push some processing down to the kernel, so you would avoid sending like packets from kernel space to user space all the time, which would potentially also help with performance. So slightly different approach than DPTK, but also maybe it has some performance advantages. So given there are no like other questions that have been submitted, that gives me a chance to ask two more. So one thing is, you mentioned in the slides or in the talk that you're also looking at heterogeneous a setup where the different servers have maybe different compute power, different memory, different networks, and that's something you can take advantage of. So it wasn't entirely clear to me how that is happening. Can you say something about that? Give a little bit more details about the heterogeneous advantages of the system in a heterogeneous environment.
Yeah. So our algorithm canary supports the heterogeneous backend servers, and that means if some server has some computation power like it's doubled of the other backend server, and we can assign a weight that is doubling, and the result is that uh, a, a double amount of traffic will go to the more powerful backend server. So to achieve this, uh, we introduce an indirection layer, like we redistribute uh, uh, normalize the random output to a weighted table, so that uh, we can take advantage of the heterogeneous backend servers, and more details can be found in our paper.
Yeah, yeah. Thanks for the answer. So just one last question. So you've been focusing on layer 4 load balancing.
Yeah.
So would this be applicable to layer 7 load balancing as well, or not?
I'm afraid if we switch to layer 7, the throughput will be a little bit degraded, because we should perform some logic, like it's no longer it may be no longer a hash table lookup. So based on that, the performance will maybe degraded, and but we are confident that our algorithm can be uh, migrated to the layer 7, at least for most scenarios of the layer 7, if we don't uh, involves some Turing-complete computations on the field.
Okay. All right. Thank you very much. So with that, we move on to the next talk. Is the next speaker here? Thank you so much. Yeah. Is the next speaker here? Okay. Hi, Marius. How are we doing?
Can you hear me?
I can hear you.
Good.
So, our next speaker is Marius Kokias. He's a researcher at MSR Cambridge, and he graduated from EPFL just this August, so difficult year to graduate. And his main research interests are at the intersection of operating systems and networking. And I also want to mention that Marius is on the academic job market. So if you have a job, or you know of a job, please reach out to Marius. So and so let me share the slides as well. So can you see the slides?
I can see them.
Okay, so then here we go.
Great. So thanks for the introduction. Hi, everyone. My name is Marius, and in this lightning talk, I'm going to present our work on CRAB. So in the next 3 minutes, I'll try to convince you that you can bypass the load balancer without regrets. This is work done with my colleague Rishabh and my advisor Ed while I was still a PhD student at EPFL. And the previous talk did a great job introducing the concept of load balancing, but there is a major difference with the previous talk. In this work, we focus on load balancing for internal cloud workloads, so workloads that run inside the infrastructure of the tenant, so of the public tenant. So we don't consider external facing load balancers. And a commonly used design and deployment pattern there is to place this kind of backend services behind the load balancer to achieve availability and elasticity. So whenever the load goes up, the service can use more machines. And also, if one of these machines goes down, then the service does not go down as well, because the load balancer will avoid this node. And there are different kinds of load balancing. I encourage you to look at the paper where we go through the alternatives and we discuss their pros and cons. But this work focuses specifically on layer 4 load balancing. So load balancing at the connection level. And a layer 4 load balancer sits...
Mario, you want me to move on with the slides?
No, not yet. I'll let you know. Yeah, thank you. So a layer 4 load balancer sits between a client and clients and servers, and assigns incoming connections to the backend servers. And after that, the load balancer remains on this data path to perform the necessary address translation and relay the packets between the two endpoints. And there are several stateful and stateless designs and implementations for layer 4 load balancers that depend on hardware and software. And these alternatives more or less try to deal with the following challenges, as it was also mentioned in the previous talk. So the load balancer should scale with the number of connections. It should be able to sustain millions of connections, and it shouldn't become an IO bottleneck. And also the load balancer should add minimal latency, a minimal latency overhead on the data path. So we don't want to increase the end-to-end latency because we load balance a service. And the last thing is that we should have a load balancer that allows updates to the server pool without breaking the per connection consistency. So let's see how we dealt with these challenges. And in our work, we introduced CRAB. So CRAB, that stands for Connection Redirect Load Balancer. So the key idea behind CRAB is that we use the load balancer only during the connection establishment, and after that, the two endpoints can communicate directly. So and by doing that, we have the following design benefits. First, with CRAB, we have a minimal, we have a significant drop in the load balancer load. So a CRAB load balancer deals only with TCP SYN packets, and as a result, we have a minimal load at the load balancer. Also, with CRAB, there is a minimal, there is almost no latency overhead in the data path. Because the two endpoints can communicate directly, we achieve close to direct communication latencies. So in CRAB, after the load balancing decision has been made, then the clients are notified that the new destination of this connection has changed, and they can talk directly. Because of that, the state and the mappings between clients and servers is distributed. So each client knows the server they're talking to, and as a result, there is no per connection state kept at the load balancer. And this enables CRAB to implement rich load balancing policies without having the scalability limitations that stateful designs have. Also, CRAB has a centralized design and enables easy updates that do not break the per connection consistency violations. So you can add and remove servers to the server pool, and this will not affect the existing connections. And the main mechanism to support CRAB is an extension to TCP that implements this connection redirection feature during the TCP three-way handshake. So we added a new option to TCP that enables CRAB load balancers to communicate their load balancing decisions with the servers and the clients, and then clients can update the destination IP of this specific connection. To do so, we implemented CRAB either through minimal changes to the TCP stack in the kernel, or through the use of net filter modules that can be used to extend a vanilla kernel. In the paper, you can see how CRAB scales better compared to the vanilla layer 4 load balancer, and how richer load balancing policies can improve the end-to-end application latency. Also in the paper, you can find a performance comparison between the different ways you can implement a CRAB middle box, ranging from a kernel-based implementation to kernel bypassing with DPDK or a BPF. And we also have an implementation using programmable switches. So this I would like to conclude my talk, and I'd like to have some questions. Thank you.
Great talk. Thanks, Marius. So let's see what questions we have. So one question that got submitted was, why is HTTP redirect not an option to bypass the load balancer?
Great. Yeah. So that's a great question. It could work under certain circumstances, but there are some main differences. The first one is that HTTP redirect works only for HTTP, while CRAB can work for any kind of layer 7 protocol. Also, with HTTP redirect, you have the extra overhead, the communication overhead, that the first connection, you have to open the first connection. The first connection, the first server says that this endpoint has been redirected, and then the client has to go and open another connection. So the connection establishment is going to be quite more expensive under this design. And the other problem with this approach is that if adding and removing servers to the server pool is going to be much more complicated, meaning that if you add a server, then you might need to notify all the servers in the group that there's a new server, that there was a new server added, and then somehow you need to coordinate the load balancing decisions that you make in this case, as opposed to having a centralized implementation that works on the data path of the connection establishment itself.
Okay. Yeah, thank you for the answer. Another question that got submitted by Preeti Marthi is the following. How does the CRAB policy know the state of the connections? For example, if a connection is still alive or dead, that type of state. And doesn't it just know that a connection was directed to a certain particular DIP?
Yeah, that's also a very interesting point. CRAB does not know that a connection was over or still running, and this is a feature that we position this as a feature because we completely bypass the load balancer after the connection is established. So for the round-robin policy, there is no need to know that a connection is over, because the load balancer will just pick the servers one after the other in a round-robin fashion. But you might want to implement the policy with something like join the list loaded server or something like that. And in this case, you will need to know when a connection is over. So instead of having the entire data path going through the load balancer, we believe that it's much better to implement an external communication between the load balancer and the server, where the server could notify the load balancer that this connection is over, and they could do that either on a connection basis or periodically. And this would open up the space for new load balancing ways to do load balancing based on different features. Because, for example, using the same communication between the load balancer and the servers, you can imagine that you can implement something which is CPU aware. So, for example, the load balancer could pick the servers that are least loaded, but not in terms of the connections or the connection throughput, but in terms of how loaded the CPU is. So, trying to decouple the two, the actual load balancing data path with the policies and the protocol that helps these policies, is something that CRAB enables, and I would like to investigate this further.
Okay. So one last question from my side. So given you take the load balancer out of the loop, right, after the handshake, and we also lose basically the capabilities to do certain things we normally like to do at the load balancer, like traffic analysis, security, and so on. So how does that play into this whole design? So how do we trade these?
Yeah, that's also a very interesting question. And the answer to that and the proposal that we have in the paper is that the extra functionality, you can implement it on the server side. So you can have any kind of firewall functionality or any kind of analytics functionality implemented in a distributed fashion on the server side, where you have the resources to do so, as opposed to doing this on a dedicated centralized middle box that should perform, it should sustain a lot of high throughput, and it should not add more latency. And the idea here is that you can use this very specialized middlebox just for load balancing, because it can have a much wider overview of the state in its server, and then it can make better load balancing decisions, as opposed to packing more functionality in this load balancing appliance. Because with this extra functionality, you don't need this centralized view.
Yeah, got it. Okay. Yeah, very interesting work. I have plenty of other questions, but in the interest of time, we have to move on. So I encourage everyone to read the paper. Thank you, Marius.
Thank you.
Yeah, let's move on to the next talk. Hi, Mohammed.
Hi.
How are you?
Thank you.
So let me open the... So our next, our next speaker is Mohamed Bilal. Mohamed is a PhD candidate at IST Portugal and also at the University of Louvain in Belgium. And his research interests are in cloud computing, distributed systems, machine learning, automation, and optimization. And I also want to point out that Mohamed is also on the job market from the end of this year. And Mohamed is going to present an interesting paper. We hear a lot about machine learning for systems and systems for machine learning, and these two big categories. This is a good example of a paper that is machine learning for systems, sort of. Let me share the slides. So, 1 second. So here we go. Can you all see the slides?
Yeah, I can see it.
Okay, here we
go. Thank you. Thanks, Patrick. I'm going to present a short summary of our work regarding selecting cloud configurations for analytics clusters. And both of my co-authors are essentially my co-PhD advisors. So can you move to the next slide, please? So the cloud configuration problem in this context is the problem to determine the number and type of instances to use when you are deploying distributed systems in the cloud. Prior work has concentrated essentially on optimizing the cloud configurations for a single distributed framework, and they are completely offline, which means that they use pre-production runs to figure out a good configuration for the environment, and then use that configuration for production runs. So the users will have to wait essentially before deploying their workload in the cloud environment. So this is already a challenging problem, and it can be tricky to find good configurations. But these frameworks are often not used in isolation. You use them in combination. So here I'm just giving an example of an analytics cluster which might be composed of HDFS, Spark, and Cassandra. You can replace it with any other type of batch processing pipeline. So in this context, the search space becomes even larger, which means that if we use completely offline methods, it can take quite long for the completely offline optimization method to find a good configuration. So can we move to the next slide, please? So this is what we are trying to tackle in this work. We essentially exploit the recurrent nature of these jobs to split the optimization process into offline and online phase. So the offline phase uses resource utilization metrics to find configurations that are good enough in terms of satisfying user constraints on execution cost or execution time. But it's not the job of the offline phase to find the best configuration. It is simply trying to find a decent configuration that the user can start their production run with. And then the online phase further optimizes cloud configuration using production runs. And we take care of the fact that it does not lead to frequent execution time or execution time violations, for example, because it is very relevant that a production run of a job does not use a cloud configuration that leads to a significant degradation in terms of execution time, or worse, it fails completely. So One-Year handles this thing online and in the online phase of it. We are able to provide comparable performance to completely offline methods, but while using half the number of offline trials. And One-Year is also twice as fast to reach within 15% of the best configuration that is eventually found within our optimization budget. And it can also handle partially bounded search spaces. And essentially, the partially bounded concept is that when you're trying to use an optimization method to figure out the best cloud configurations, you have to specify the number of instances and the type of instances, the range within which the optimization algorithm can work with. And with partially bounded search space, we essentially remove the limit to specify the maximum limit on the number of instances. So One-Year will still handle that search space, even if you don't specify the maximum number of instances. So that's a very short summary of the work. More details of implementation and everything else is in the paper. Please take a look at it. And if you have questions, I'm happy to take. Thank you.
Great talk, Mohammed. Thanks for that overview. I don't see any questions that have been submitted beforehand, also not on the Zoom chat, but I have a few questions. So one thing I noticed when I was reading the paper, and you correct me if I'm wrong here, is that the way the resources are tuned is rather coarse-grained. So you're basically coupling memory and CPU. You add another virtual machine and you're basically adding compute power, memory, and so on. Would it make sense to do the resource management in a more fine-grained manner so that you can scale different resources independently?
So that's a good question, and I think because in this case we were using the VM instances directly. Most of the cloud providers do not allow you to do it, other than Google Cloud. Google allows you to configure memory to independently configure the number of CPUs and the amount of memory that you can allocate to an instance. But in a setting like if we were deploying it on top of Kubernetes, for example, then I think it's definitely applicable that maybe we want to only change the memory limit of the containers on which we are running a particular framework instead of changing both the CPU and the memory. Does that answer the question?
Yeah. So the tools are sort of limited, you're saying?
Yes, in terms of when you're deploying it in a VM, but I think on a Kubernetes cluster, you might be able to do something along those lines.
Okay. So another question I have is when you do performance, so you look at reoccurring jobs, right? And you try to see if it's a similar job than a job that has been running previously. And you're also looking at the resources a job is consuming at the given point in time. But how difficult is it to do this if jobs are running concurrently? So there might be multiple jobs running concurrently, and it's difficult to figure out to attribute the resource consumption to a particular job if they are running concurrently. How you isolate that?
Yeah, so I think you're talking about a multi-tenant setting, right? So it depends on how you're deploying these jobs, right? If you're setting up clusters, a single cluster that runs all your jobs, I think it will become quite tricky to attribute the performance, especially when the tasks of different jobs are sharing the resources. But in a cloud environment, you can essentially spin up clusters individually for these things. With DevOps, you have the capability to spin up the cluster very, very quickly, rather than having to have a static cluster that you're perhaps using for all your jobs. So we do not follow a multi-tenant setting in this case, but I think that's still fine, because you can spin up an individual cluster for a job. It's very quick to spin something like that up. But definitely in a multi-tenant setting, it might be quite tricky to use resource utilization metrics essentially to figure out which tasks of a job are consuming the resources in this case. So that could be an interesting direction to see in scenarios where multi-tenancy is very critical for one reason or another. Yeah,
thank you for the answer. So out of curiosity, I'm also wondering, so in this pipeline, in this world where you have like multi-pipeline jobs, are you assuming the different stages in this pipeline are running on separate clusters, or can they be run on the same cluster?
I suppose you mean on the same set of nodes, right? So the scenario that we have, we are separating the nodes on which different frameworks are being deployed. And that's essentially because of ease of capacity planning. So you can capacity plan them individually. You can deploy them together in a setting, but then it becomes very tricky to figure out the right capacity for different parts of your pipeline. But there is another scenario that we discussed in the paper. Instead of these multi-tenant settings, instead of these different framework settings, we could also have a pipeline of batch jobs. And in that case, they could be essentially running on the same set of scale cluster with every particular job. So that in that case, I think you can still apply the same techniques that we have used.
Okay, I was just wondering the initial figure you had on the first page where you have Hadoop, Spark pipeline, Cassandra pipeline, and so I would have assumed that at least the Hadoop and Spark jobs, if there's such a setup in practice, that those two frameworks will be to run on the same cluster.
Yeah. In this case, since this is a specific example that we use, we do not co-locate them. But if we want to enforce co-location, that would be an interesting thing to deal with.
Okay. All right. I think that brings us to the end of this session. Thank you very much for the talk and the questions and for the answers.